Here in front of us, we have a sinusoidal signal. And this signal is called a periodic signal because it repeats itself. Here in green, I'm going to mark a point in the signal. And I'm going to follow the signal. It goes to 0, comes back to 0, and comes back to this point. So you see, it reaches a certain magnitude of, let's say 2. So it reaches a magnitude of 2 again and again. So this signal keeps going. And so because it repeats itself, because it keeps coming back to magnitude of 2, this signal is called a periodic signal. I'm going to write it here. And every periodic signal has a certain property called a time period. So here I've referenced 2, and the time this signal takes to reach to a magnitude of 2 again is called the time period. So if it takes 2 seconds to reach 2 again, this signal has a time period of 2 seconds. So if you are dealing with oscilloscopes and you observe a signal, in oscilloscopes, it's some of the newer ones, it's very easy to reference these points. So that's how you measure the time period. You mark one point, and then you measure the time the signal takes to reach that point again, and that is going to be your time period. Now, another property that most periodic signals have is called frequency. So frequency is the number of cycles in 1 second. So just follow this. So this signal starts at 0, goes, reaches magnitude 2, comes back to 0, and hits 0 again. So from this point onwards, it's a different signal. So this is the second cycle of the signal, and it goes. So the number of cycles, this is 1 cycle. So let me write it down somewhere here. All right, so this is 1 cycle up to this point, and this is second cycle. And the signal is going to have infinite number of cycles till you stop it. So the frequency is the number of cycles you have in 1 second. And there's an easy formula to find the frequency. It's just 1 over your time period in seconds. And its unit is hertz, named after hertz. So if you know the time period, you just inverse it, and you get your frequency that way. So very simple. Now let's look at the expression for this signal, and here I've considered a voltage signal because it's one of the most commonly encountered signals in electrical engineering, because most of the time either you're measuring voltage or you're measuring current. Alright, so this waveform that I've shown here has an expression Vm sine omega t plus phi. So Vm is the peak voltage. So if I have a signal like this, what's the peak value it reaches? That is Vm. I'm gonna delete that messy diagram. And another term here that you gotta look at is omega. It's not just a W, it's a Greek alphabet omega. And that is known as angular frequency. So it's kind of related to it's kind of like a speed, how you measure speed of your car. So sort of like measuring the speed of your signal. So this angular frequency omega is given by the expression 2 pi times frequency. Omega is, because frequency is just, as we saw here, 1 over time period. So this can also be written as 2 pi over your time period t. And the last term we're going to look at is something known as phase shift. So if you look at this signal here, it starts right at 0, right? But if you have a signal that is somewhat off, it doesn't start at 0, so it starts at a certain point after 0, and it's going to go back. So this signal is phase shifted, and so that is a measure of phase. The phi term here is the phase shift. So if you have a 0 degree phase shift, it means the signal starts at origin. So if you have 180 degree phase shift or a pi radian phase shift, it starts at exactly the half value. All right, now let's go ahead and look at some more terms that we're going to come across. So here I have this beautiful diagram that I stole off the internet, and we're going to look at some terms. So as I already mentioned, the peak value is the maximum voltage that it can acquire. So this is the peak value. And based on that, for a periodic sinusoidal signal, we have a value called the RMS voltage, or the effective value. So the expression for your Vrms or V effective is just your V peak times V peak is denoted by Vp divided by root 2. So this is very important expression that you would probably use in solving most of the problems. So Vp, your Vrms is your peak voltage divided by root 2. And here let's look at another term. So especially if you're dealing with oscilloscopes, you'll measure also V peak to peak. So that is your positive peak to your negative peak. So that magnitude is known as peak to peak voltage. And there is also average voltage, which is the area enclosed within the curve. So it kind of finds like what is the average value of the signal over a certain period of time. And there's also an expression for that, but we're not going to worry about that. All right. And let's dive into our problems. So another thing I wanted to mention was when you use your multimeters to measure a sinusoidal waveform, they're measuring your RMS voltage. Right? So your multimeters pick up your RMS voltage. All right, so without further ado, let's move on. But before that, let's do a quick recap. This is a periodic signal. The time it takes to reach the original point is called the time period. The number of cycles in 1 second is called the frequency, and it's just 1 over your time period. And we saw what is a peak voltage, the general expression, and also another thing is this sign can also be a cosine. So cosine term can also be used. Some signals are generally described as sine and cosine because sine and cosine are interchangeable. So if you visit your basic trigonometry, you'll realize that sine and cosine are just phase shifted by 90 degrees. So they're interchangeable signals. And we looked at what is the root mean square term, and it's just your peak voltage divided by root 2. And it is the voltage measured by most voltmeters or multimeters when you try to measure AC signals. Okay. Here we come to our first problem. So our first problem, the statement says the effective voltage is 10 volts. So I got to find the maximum voltage. So that is V max. So let me draw this out. So assuming we have a periodic sine wave, it says the effective voltage is nothing but your RMS voltage. So it says the RMS voltage is 10 volts. And now we gotta find what is the maximum. What is this point? What does this measure? So that is my peak voltage. So if we're going to make use of this very simple formula. So your RMS voltage is your peak voltage divided by root 2. So in order to find peak, you just multiply the RMS voltage times root 2. So that's 10 volts times root 2 is 1.414. So it's just 14.14 volts. Very simple. But just remember, guys, you never measure V peak unless it's in an oscilloscope. So if you have an oscilloscope and you're measuring a signal, that's the only time you get to see the peak voltage. But otherwise, if you're using multimeters, voltmeters to measure signals, you're always looking at the RMS voltage. Very important to note when you're dealing with AC circuits. All right, let's go to the next problem. Very simple problems. This problem says we got two signals. We got one signal which is 10 cosine 500t and another signal 15 cosine 100t plus 45 degrees. So the 45 degrees, if you remember, this was the phase shift. So this signal, we have one signal that's got a magnitude of 10, and because it's a cosine wave, it starts somewhat like this, and it goes on. So it starts exactly at 0. And we got another signal, this one right here. It starts at 15, and it's got a speed of, it's wrong to call it speed, angular frequency, but it's relative to your speed in your cars, somewhat like that. And it starts 45 degrees after 0. So if this is 0, 45 degrees is pi by 4. So this is where the cosine wave starts, and it goes on. So those are your two signals. And we got to find the algebraic sum of these two signals. Let us consider this second signal first. So we got V2 is 15 cosine 100t plus 45 degrees. And we're going to solve this. And we're going to solve this and simplify it using an expression that is, if you remember your trigonometry, cosine A plus B is cosine A times cosine B minus sine A times sine B. So here our A is just 100t and our B is 45 degrees. So our V2 is going to be 15 times, I'm going to open this bracket, cosine 100t and cosine 45 degrees minus sine 100t and sine 45 degrees. Now sine 45 degrees and cosine 45 degrees is just 1 by root 2. So the value is is equal. So this would be 15 times cosine 100t by root 2 minus sine 100t divided by root 2. Okay, so we simplified our V2 signal. Now the sum of these two signals is just going to be 10 times cosine 500t plus 15 over root 2 in this signal right here. I'm going to write it here. Okay, that was a little messy. Let's go ahead and simplify this a little bit further. So it's going to be 10 cosine 500t, and 15 over root 2 is 10.6. So that is our signal right here. So what is the significance of this problem? We're not just randomly solving some problems. There is always some significance attached to it. So we got two sinusoidal signals, and they're not exactly equal. So if you have these two interfering with each other, your resultant waveform is going to be this final answer that we got. So the way to find the resulting waveform, I'm just going to quickly show you, I'm not going to do it exactly, is you got to substitute different values of t and then solve the entire equation. And then for that, you would get different values of magnitude and you can plot the wave. So I'm just going to do it for t0. So for time t is equal to 0, your cosine terms are going to be 1. And your sine term is going to be 0. So this term we're not going to consider. And it's going to be 10 plus 10.6. So that's 20.6. So at time 0, your waveform is going to be here. And it's going to follow some pattern. And so that is called the superposition of waves. So you just take the algebraic sum and use, from this expression, you can tell at any period in time what is the magnitude gonna be. All right, our next problem statement says we got a signal 100 cosine 500t plus 50 degrees. It's phase shifted by 50 degrees. And we got to find the frequency of this signal. So let's write this signal down. 100. So the signal, I'm not going to name it anything. Okay, let's, for the time being, consider this a voltage signal. So it's 100 cosine 500t plus 50 degrees. All right? And remember, the expression is so if you look at the terms, 100 is the maximum point of the signal. So if I'm assuming it's a voltage signal, it's going to be 100 volts or millivolts. It's not going to be 100 volts for sure. So that's the maximum voltage. And your omega is 500 radians per second. Or because it's given in degrees, so it's going to be a different value. So your omega is 500. So omega is nothing but 2 pi times frequency. Remember, it's kind of like measuring how fast your signal is going, how fast your signal is. So you're measuring it by this term omega. So that's an indicator of 100 is an amplitude indicator. And omega term here is a speed or a frequency indicator. So this omega term is just 2 pi f. And so from now, it's very simple. So your frequency is just going to be 500 divided by root 2 pi. And you get an answer for this as 250 by pi. And that is going to be 79.5. And the unit for measuring frequency is hertz, because it's all in seconds, so it's just hertz. All right, cool. Let's go on to our last problem. So there is another periodic waveform shown here, but it is not sinusoidal. So this is a square waveforms, sort of step functions. So the expression for this waveform can be written in the form of step functions, but that's a topic for another lecture. But let's go ahead and solve this. And I'll show you why it's called a periodic waveform, because I'm going to consider this point here where it reaches a magnitude of 2. So it's going to reach a magnitude of 2 again here. So, hey, and it takes a time of 5 minus 1. So this is 4 seconds. So it has a time period of 4 seconds and a frequency of 1 over 4. So that is going to be 0.25 hertz. But we're not being asked to calculate any of that. We are being asked to find the average value. Now the average value is, I'm going to denote this signal as A. Average is going to be 1 over time period t, integral 0 to t, and the value, magnitude of the signal, I'm going to take it as x. I'm just considering x. Okay, so if I have that as x, so this is going to be x as well. So x of t times dt. So very simply, what I'm doing is, an average is just the sum divided by the individual components. So here, this part is looking at what is the total of the signal. So the total magnitude of the signal is obtained by integrating it over a period of time, and then dividing it by that time gives you what is probably going to be the average value of the signal in one time period. So let's go ahead and solve this. So your x, average value of x, let's break it down. Okay, so we got time period is 4 seconds. So it's going to be 1 over 4. And an integral 0 to 4. And this part is a little tricky. You got to find x of t for one time period. So let's start from 0 to 1. I'm going to break it down. Okay. So since I'm breaking it down, what I'm going to do is break down the integral to. It's way simpler to do it this way. So from 0 to 1 second, we got the signal going here, right? So let's follow this. It's at a magnitude of 1. So your value of x is just 1 for 0 to 1 times dt. Now let's go from 1 to 2. So from 1 to 2, the value of your signal, the magnitude of your signal is 2. So it's going to be 2 times dt. And from 2 to 3, the value of your signal is again 1. And lastly, let's not forget this because this is one cycle. So if you look at this point, if you consider this point as the starting point, if you consider this point as the starting point here at 0, the signal doesn't end here, but it ends at 4. Because the time period is 4 seconds. So that's another way to check. So if you look at, most people make the mistake of considering this signal as a signal having time period of 3. But no, it's a signal having time period of 4 seconds. That's why I showed you with reference to the point shown in green. So from 3 to 4 seconds, the value of your signal is just 0. Okay. So if we go ahead and solve this integral, I'm going to go to a new page, is 1 over 4 your integral of 0 to 1 times dt is just 1. Because the way this works, I'm going to show you. Real quick math lesson here. The way to integrate this is going to be 1 is going to come outside, and then the integral of dt is just going to be t, and this is going to go from 0 to 1. So this is going to be 1 minus 0, and that is just 1. Okay, so that was a really quick math lesson. Let's do that for all of these signals. So it's going to be, I'm going to rewrite this signal here again. So average value was 1 over 4 integral 0 to 1 over dt plus 1 to 2, that was 2 times dt, plus 2 to 3, that was 1 times dt, plus 3 to 4 plus 0 times dt. So this is going to be 1 over 4 as I showed you. So this value is going to be just 1, and this is going to be 2, this is going to be 1 again, and it's going to be 0. So that's 4 over 4. So this average value is going to be just 1. So the average value of this signal, it's a step function, it's a complicated step function. A sum of step functions is, if you want to know what's the average, so this signal goes from 0 to 2 depending on the time. So the average of this signal is just going to be 0. So on average over a period of 4 seconds, sorry, it's not 0, it's 1. Sorry about that. So it goes from 0 to 4 seconds. It starts off at 1, then it jumps to 2 at 1 second, jumps back to 1 at 2 seconds, and goes to 0 at 4 seconds. So over a period of 4 seconds, this signal has an average value of 1. Right? Alright guys, that is it. Thank you for watching. Good luck on your Fundamentals of Engineering exam, and see you in the next video.